What happens when you stop looking at the universe? No, seriously. If you stare at an apple on the table, you know it's there. But the moment you look away, does it still exist as a solid object? Or is it just a fuzzy cloud of possibilities waiting for you to turn back and force it to decide? Sounds ridiculous, right? But in quantum mechanics, this is a real problem. Because at the smallest scales, things don't just exist the way we think they do. They act like waves, probabilities, until you measure them. Then, suddenly they snap into place as if reality was waiting for you to show up. This isn't some sci-fi mind trick, it's called the observer effect, and it's one of the weirdest, most debated concepts in physics. But does it really mean you're changing reality just by looking, or is something else going on? Alright, so let's talk about the experiment that shattered our understanding of reality, the Double-Slit Experiment. If you've never heard of it, prepare to question everything. If you have, well, let's make sure you actually get how weird this thing really is, because most people don't. Here's the setup. Imagine you have a wall with two tiny slits in it. On the other side of the slits is a screen that will record whatever passes through. Now let's say you grab a handful of tiny particles, electrons, photons, whatever you like, and fire them toward the slits. What should happen? If these particles are little solid objects, like tiny bullets, you'd expect them to go through one slit or the other, landing on the screen in two neat clusters, right behind the openings. But if they're waves, they should pass through both slits at the same time and interfere with themselves, creating a striped pattern. An interference pattern, where some waves cancel out and others combine. So which is it? Particles or waves? When scientists first ran this experiment, they expected the particles to behave like, well, particles, hitting the screen in two neat bands. But when they checked the results, they didn't see that. Instead, they got the interference pattern. That meant the electrons were acting like waves, passing through both slits at once and interfering with themselves. Here's the problem. Electrons indeed behave like particles. You can hold an electron in a trap and measure its charge, so why are they suddenly behaving like waves when they travel through those slits? Physicists thought, alright, maybe we just don't know which slit each electron is going through. Let's set up a detector to watch them. That should settle it, right? Wrong. The moment they placed a detector near the slits to observe the electrons, something crazy happened. The electrons stopped behaving like waves and started acting like normal particles. No interference pattern, just two neat clusters, as if each electron suddenly chose a single slit to go through the second it was measured or observed. Let's break this down. When there is no observer, electrons go full-on wave mode, passing through both slits at once. But when an observer is watching, electrons stop messing around and act like regular particles, choosing a single path. Something about measuring the electrons forced them to behave differently. But why? This experiment is not just some minor quirk of physics. It suggests something disturbing about the nature of reality. It tells us that before measurement, particles don't seem to have a definite state. They exist as a wave of probabilities, spread out in multiple possibilities at once. It's only when we try to measure them, when we observe, that they suddenly decide on a definite state. Think about that. It means that at the quantum level, things don't exist in a clear, defined way until they are measured. It's as if reality itself refuses to commit to a decision until it's forced to. This isn't just a physics problem, it's an existential one. What is reality, really? Does it exist independently, or does it need an observer? And most importantly, why does the universe seem to care whether we're watching? So, what is actually happening? At this point, the double-slit experiment has left us with a huge question. Why does observing something change its behavior? Why does the wave function collapse upon measurement? Do they know they're being watched? This phenomenon, known as the measurement problem, is one of the deepest questions in quantum mechanics. It challenges our understanding of reality itself. How and why does a system, existing in a superposition of possibilities, suddenly settle into a definite state the instant we observe it? Let's clear up a common misconception right away. This has nothing to do with human consciousness. You're not bending reality with your mind. It's not like the universe is waiting for you to wake up in the morning before it decides whether your bed exists. The change happens not because someone is thinking about the electrons, but because measuring them physically disturbs their state. To understand this, we need to talk about what measuring really means in quantum physics. In everyday life, when you measure something, like checking the temperature outside, you're just gathering information. You're not changing the weather by looking at a thermometer. But in quantum mechanics, measuring something isn't just passive observation, it's an interaction. When we try to look at a particle, we have to hit it with something, like a photon of light. And here's the problem. Particles are small. Really, really small. Imagine trying to find out where a ping pong ball is in a dark room, but the only way to check is to throw a basketball at it. The moment your basketball hits the ping pong ball, it's not in the same place anymore. You can know where it was, but now you've lost track of where it's going. This is exactly what happens with electrons. The act of measuring their position disturbs them so much that it changes their state. The primary goal of measurement is to gain information about the state of the system. This information comes at the cost of altering the system's state, which is a key difference from classical measurements where one might measure attributes without fundamentally changing the system. Also, the measurement apparatus itself becomes part of the quantum system during measurement. In some interpretations, like quantum decoherence, the environment plays a crucial role in making the measured state classical or definite by entangling the quantum system with a vast number of environmental degrees of freedom. In other words, the observer effect isn't about your consciousness, it's about physics forcing reality to pick a side. At the quantum level, particles don't have a set position or path until they're measured. Instead, they exist as a probability wave, meaning they could be in multiple places at once. This is called a superposition, or possible states exist simultaneously until something forces a decision. Measuring a particle forces this wave function to collapse. It's like the universe rolling the dice and picking a single outcome. Before that, the particle isn't in any one place. It's just likely to be in different places with certain probabilities. But the moment we interact with it, the wave function collapses and the particle settles into a definite state. This is why, in the double-slit experiment, when there is no measurement or observation, the electron or any quantum particle remains in a superposition state, behaving as if it's a wave. This means it passes through both slits simultaneously, leading to an interference pattern on the screen, which indicates that each electron interferes with itself. And when a measurement is made, for example by detecting which slit the electron passes through, this interaction causes the wave function of the electron to collapse. As a result, the electron behaves like a particle, choosing one path or the other, and the interference pattern disappears. Instead, you observe two distinct bands on the screen, corresponding to the paths through each slit. It is not that the electron was consciously choosing what to do, it's that it never had a definite state to begin with, until we forced it to make a decision. Here's the really weird part. If particles don't have a definite state until measured, does that mean reality itself is unfinished until something interacts with it? Is the universe just a set of probabilities waiting to be observed? This is where things get philosophical. Some physicists argue that the world only seems real and solid because we constantly interact with it. Others suggest that reality only becomes definite when enough particles interact in a way that cancels out quantum uncertainty. But the deeper question remains: if nothing were watching, measuring, or interacting with the universe, would it even exist in a definite form? And that's where things get really strange. So, we've established that measuring something in quantum mechanics isn't just about looking, it's about physically disturbing it. But things get even weirder when we realize that there are limits to what we can even know about a particle. Enter the Heisenberg uncertainty principle, which basically tells us, pick one, position or momentum, you can't have both. This isn't just a problem with our measuring tools, it's a fundamental law of nature. The more precisely you know where a particle is, the less you know about where it's going, and vice versa. No matter how advanced our technology gets, this uncertainty will always be there. Alright, imagine you're watching a race car on a track. If it's zooming past at 200 miles per hour, you know its speed, or momentum, pretty well. But if you try to pinpoint its exact location at any given millisecond, it's basically impossible. It's moving too fast to freeze in place. Now imagine the opposite. If the race car is parked, you know exactly where it is. But now you have no idea how fast it's going because, well, it isn't moving at all. At the quantum level, particles don't have both a definite position and momentum at the same time. The more precisely you try to measure one, the more uncertain the other becomes. But why? The key is that, at the smallest scales, particles don't behave like tiny marbles rolling around. They exist as waves of probability, which means their exact position and motion are inherently spread out. When we try to force them into a definite state by measuring one property, like position, we disturb the other, momentum, so much that it becomes unpredictable. Here's why. If we try to trap an electron in a small space, precise position, its momentum becomes wildly uncertain. If we try to measure an electron's momentum precisely, its position becomes so spread out that it could be anywhere. It's not that our instruments aren't good enough, it's that nature itself refuses to let us pin down both at the same time. Think about how we normally understand reality. In classical physics, if you know where something is and how fast it's moving, you can predict exactly where it'll be in the future. This is how we send rockets to space and predict the motion of planets. But at the quantum level? Nope. The best we can do is assign probabilities. Instead of saying, this electron will be here, we have to say there is a 70% chance it's here, a 20% chance it's over there, and a 10% chance it's somewhere else. This completely wrecks the idea of determinism, the belief that if you have all the information about a system now, you can predict its future exactly. In the quantum world, randomness is baked into reality itself. Does this mean reality is just a guessing game? Well, kind of. This uncertainty principle tells us that at a fundamental level, nature isn't precise, it's probabilistic. Particles don't have exact positions or velocities until they're measured. Before that, they're just a cloud of possibilities. But here's where things get unsettling. If uncertainty is a built-in feature of the universe, then does that mean randomness is at the heart of reality? Is the universe making things up as it goes? And if that's the case, how much of what we think is solid reality is just an illusion of certainty? Does this mean reality is an illusion? At this point, quantum mechanics is throwing reality into question. The double-slit experiment tells us that particles behave differently when observed. The uncertainty principle tells us that we can't even fully define reality at the smallest scales, so a natural question emerges. If things don't have a definite state until they're measured, does reality even exist when no one is looking? This isn't just a physics problem, it's a philosophical nightmare. Because depending on how you interpret quantum mechanics, the answer might be, maybe not. Scientists don't fully agree on why measurement changes reality, so there are several interpretations of what's happening. Some of the most famous ones are the Copenhagen interpretation. This is the mainstream view, championed by physicists like Niels Bohr. It says that particles exist in a superposition of states, meaning they aren't in any one specific place until they are observed or measured. The act of measurement forces the particle's wave function to collapse, making it settle into one reality. Basically, reality doesn't exist in a definite form until something forces it to make a decision. This is what leads people to ask unsettling questions like, does the moon exist if nobody is looking at it? Bohr's answer? Don't ask. Next we have the many worlds interpretation. This one is both cool and terrifying. Instead of collapsing into one reality, what if every possible outcome happens but in separate universes? This is the many worlds interpretation proposed by Hugh Everett. According to this view, when you measure a quantum system, reality splits into different versions. In one universe, the electron went through the left slit. In another, it went through the right. And in another, well, you get the idea. If this is true, then every choice you make, every coin flip, every missed bus, every embarrassing thing you've ever done has played out in infinite parallel worlds. Somewhere out there's a version of you that made all the right decisions, but there's also a version that still thinks cargo shorts are a good idea. And then we have the pilot wave theory. Physicist Louis de Broglie proposed a different idea. What if particles always have a definite position, but they're guided by a hidden pilot wave that we can't directly observe? This would mean that reality is definite, but we just don't fully understand how the underlying mechanics work yet. This interpretation is interesting because it lets us keep a solid, classical-style reality, but at the cost of accepting that there's an invisible layer of the universe we can't see. It's like physics with cheat codes. The rules work, but there's a hidden mechanic running the whole system in the background. So, is reality fake or not? The short answer? We don't know. The slightly longer answer? It depends on what you mean by real. If reality requires things to have definite properties at all times, then quantum mechanics suggests reality is kind of incomplete. But if reality is just what we observe, then maybe everything is fine. We just have to accept that at small scales, things are weird and uncertain. But here's the really weird thought. If reality is only definite when observed, then who or what is measuring the universe? Is the universe constantly watching itself? Are we all just probabilities waiting for some cosmic observer to collapse us into existence? And if we ever stopped looking, would everything just fade back into uncertainty? At this point, the idea that reality only becomes real when observed is unsettling enough. But this brings us to an even weirder question. Does it have to be a conscious observer? Could it be that human consciousness itself is what collapses the wave function? That our minds are actively shaping reality? That the universe on some level is waiting for us to notice it before deciding what's real? This idea isn't new. Some people, often misinterpreting quantum mechanics, claim that the mind directly influences reality, that the universe bends to our will just because we're aware of it. Sounds profound, even mystical. But is it true? Let's be clear, no mainstream physicist believes that consciousness is required to collapse a quantum wave function. The idea that a thinking mind is necessary for measurement is largely a misreading of quantum mechanics. The confusion started because early quantum pioneers like John von Neumann and Eugene Wigner considered if consciousness played a role in measurement. Wigner even suggested that maybe a conscious mind is required to turn quantum potential into actual reality. But later experiments showed that collapse happens even without a human observer. Machines, detectors, and even interactions between particles themselves are enough to force a quantum system to take on a definite state. Reality doesn't need you to look at it, it just needs something to interact with it. A common way people misunderstand the observer effect is by thinking it means your thoughts are controlling reality. But let's test that idea with a simple experiment. Imagine flipping a coin and willing it to land on heads. No matter how hard you focus, quantum mechanics doesn't let you control the outcome. The universe is not taking orders from your brain. If consciousness directly collapses wave functions, then theoretically you could choose the outcome of quantum events just by thinking about them. But every test of this idea has shown that randomness still wins. Quantum mechanics is weird, but it's not a magic spellbook. If it's not consciousness, why does reality behave differently when we measure it? Here's the real answer. It's the act of measurement itself that matters, not the person doing it. The reason an electron behaves like a wave when unobserved and like a particle when measured is because measurement is a physical process that disturbs the system. Imagine a pool table in a dark room. If you want to see where the balls are, you need to shine a flashlight on them. But in doing so, you're adding energy to the system. You might nudge your ball slightly by illuminating it. The same thing happens in quantum mechanics. When we measure a particle, we physically interact with it in a way that forces it to take on a definite state. The observer in the observer effect isn't some mystical consciousness, it's any interaction that forces a choice. Here's where things get really strange. If quantum particles need to be measured to take on a definite state, then what was happening before any conscious life existed? If nothing was around to observe the early universe, was it just an ocean of probabilities waiting to be measured? This leads to some interesting ideas. Maybe the universe itself is its own observer. The interactions between particles, forces, and fields could be constantly measuring each other, keeping reality in a definite state. Or maybe measurement happens at a fundamental level, the moment a particle interacts with another particle. That's enough to count as an observation. Or maybe our concept of reality is incomplete. If we need to measure something for it to exist in a definite state, what does that mean if there are still parts of reality floating around in uncertainty, waiting to be observed? It's possible that the universe doesn't need conscious observers at all. Reality doesn't rely on human attention, it just needs interactions to make things real. But here's the kicker. If we ever find out that consciousness does play a role in measurement, that would mean our minds are directly tied to the fabric of reality itself. And that would be one of the most profound discoveries in human history. At this point, we've gone from quantum weirdness to questioning whether reality even exists when we're not looking. We've ruled out the idea that consciousness is required for measurement, but we're still left with a much bigger question. What actually defines reality? If particles don't have fixed properties until they interact with something, then is reality just a shifting sea of probabilities? And if observation, whether by a machine, another particle, or even the universe itself, is what forces things into a definite state, then what does that say about the nature of existence? If reality only becomes real when measured, then what about the parts of the universe we haven't observed yet? Take a galaxy billions of light years away. No human has ever seen it up close. No telescope has ever directly measured every single one of its atoms. So before we observe it, is it just a set of probabilities? Or consider this. If you leave your house and go to work, do the walls of your home remain exactly as they were, or do they return to some kind of quantum blur until you walk back in? This sounds absurd because in our everyday world, things stay put whether we look at them or not. But at the quantum level, we know that until something is measured, it remains in a state of uncertainty. You've heard the classic question, if a tree falls in a forest and no one is around to hear it, does it make a sound? Quantum mechanics forces us to ask an even weirder version. If the tree is never observed at all, was it ever in one definite state to begin with? And if our entire reality is just a collection of quantum systems, does that mean everything is in an unresolved state until some kind of observation forces it into place? The weird thing is, physicists don't fully know the answer. Some say the universe is constantly measuring itself through interactions between particles. Others argue that we don't even need wave function collapse. Maybe all possible states exist at once, and we just experience one version of reality out of many. Some theories suggest that the reality we experience is just a projection of something more fundamental. The holographic principle, for example, suggests that everything we see as three-dimensional might actually be encoded on a two-dimensional surface at the edge of the universe. In other words, what if our perception of reality is just an illusion, a simplified version of something much more complex underneath. Think of a video game. When you play, you see a detailed world with trees, oceans, and buildings. But behind the scenes, it's all just lines of code determining how things behave. You can't see the code, you just see the game world. What if the universe is like that? What if everything we perceive is just the surface layer of something deeper, something we can't directly measure? We can see and experience what is happening in the universe, but we don't seem to grasp what is going on. While we have developed rules and theories to describe phenomena at the quantum level, the why behind these behaviors remains elusive. Does reality exist independently, or is it somehow shaped by observation? Are we in a situation where these rules are just the programming code? This is where the infamous simulation theory comes in, the idea that what we think of as reality might just be a kind of programmed system. Some scientists have even suggested that the strange, rule-based nature of quantum mechanics could be a sign that we're living in a computational universe, like a cosmic video game running on some ultra-advanced hardware. Of course, this is speculation, but quantum mechanics does seem to suggest that the universe is not as solid as we once thought. If everything at its core is just probabilities, then in a way, reality is less like a physical object and more like a shifting equation waiting to be solved. Quantum mechanics has given us a set of rules for how reality behaves at the smallest scales, but it hasn't answered the deeper question of why things work this way. We still don't fully understand whether reality is independent, observer-dependent, or something stranger altogether. But here's one thing we know: the universe is weirder than we ever imagined. And maybe, just maybe, we're still only scratching the surface of what's really going on.